Hello, everyone. So today I will give an update of the Apache Gluten project. So I like the name, Save the Union Apache Gluten. So the gluten is used to combine the Spark and the Velox. So it offloads the Spark SQL engine to Velox SQL engine to get the performance. Today, I will cover several topics. First, it's a simple introduction. I already introduced many times in different forum, but there are some new people today. I'd like to introduce a little more. And then it's the current status of the functionality, community, and the customer adoptions of Apache Gluten, and then some performance data and the roadmap of 2025 this year. This is a Gluten overview. Gluten itself, it's a Spark plugin. So it's a Spark plugin. It's reuse Spark. It's a Spark user transparent. So the reuse Spark control flow and added several components into the Spark. So one is the plan conversion, convert the Spark plan to the substrate plan, and the second one is the memory management. It's you reuse Spark memory manager, but it controls the memory location over the Velox. And the columnar shuffle is a big part of the Spark. And then it's similar. And similar is used to support different Spark versions. And the fallback, because Gluten is designed not to replace all the Spark SQL engine. We cannot actually, because of the UDF and the operators we haven't implemented. So for those unsupported features or operators or functions, we have to fall back to vanilla Spark. And then it's the metric. Metric is very useful. Metric is here. The metric is taken from the native SQL engine and show in Spark UI to quickly identify what's the bottleneck of the Spark SQL operators. And under Apache Gluten, we have support different plugins. Firstly, it's the Velox, of course. We already support now. We worked with Meta very closely on the Velox. And then it's a ClearHouse. Actually, Gluten have the ClearHouse backend as well. It's used by Collegians. And we all use the substrate plan and pass the substrate plan to the different native SQL engine. That's the common part we use. And also, we support the Apache General Computer. It's currently we only use the CSV scan in Apache Angular, and then it's FPGA accelerators. We are working. So this is how the Apache Gluten works. Firstly, we use the Spark has the driver node and the work node. In its work node, it has the executors and different task threads. We all know that. And also, they have a Spark block manager to handle the shuffle things. What Gluten does is inside of each task, we check this operator is supported by native SQL engine or non-native library or not. If it's already supported by native library, we send this operator to the native library and execute it and return the data. If it's not supported, then we fall back to vanilla Spark GVM SQL engine. And we reuse the Spark control flow. We didn't do anything about the Spark control. We reuse the Spark shuffle. We use the catalyst optimizer, everything. We just offload the Spark SQL, the data processing to the native SQL engine because the data processing is a bottleneck. Here is a simple journal of the Gluten. We actually started Apache Gluten. We started the Grill project back to 2019. It's 5-6 years ago. And in 2021, end of 2021, we noted that the Grill project cannot go on because our team developed the Apache Arrow-based SQL engine. It's very hard. Its performance is not good. Lots of issues. So we moved to Velox in 2021. End of 2021, we started the Gluten repo, and in December of 2021. And you may note that Photon is released in 2020. It's in October 2021. So we actually start Grill before the Photon project released. And then we spent half a year to pass the TPC-8, 6 months past the TPC-DS. Then we focused on the performance improvement of the TPC-8, TPC-DS from 2.3 to and 1.3 to until three times and more than two times of TPDS. Meanwhile, we added some more urgent features like data like support, basic data like support, the CPU support, UDF frameworks support. And in 2024, last year, since last March, we have several big features implemented here. So in March, we have in August, before August, we implemented a salt-based shuffle. So previously, we used hash-based shuffle always. The Spark hash-based shuffle have a big issue is that we have to allocate the memory before when we split the branch. And if the shuffle partition size is very large, then we will have a lot of small split, small branches, and the memory is not enough. And the shuffle data size, because each branch, each shuffle data is the partition is too small, and it leads to even larger partition, larger shuffle data size. So in August, in last year, we implemented the salt-based shuffle. And we also implemented fire test over vanilla Spark versus Velox to verify if the Velox functions can work correctly. And later, we implemented SMG support. So before that, we only supported hash-based sign. For the salt merge join, we offloaded to vanilla Spark, but later we implemented that. We also uploaded the perf script. And the partial project is used to solve the UDF issues. So when you have a project, and the project only have one UDF, all the other operators, all the other functions is already implemented in Velox. In this case, without this feature, we have to fall back our project to vanilla Spark. And before the fallback, we have to do a column to row. And after the fallback, we have to do a row to column, vice versa. So before the fallback, we have to do a column to row. Yeah, and after the fallback, we have to do a row to column because they use different data format. And the column to row to column it's expensive actually. It's not only the copy mem copy, it's expensive, and sometimes it's even have its penalty is even bigger than the project itself. So with the partial project, what we do is that only for bank this operator or is this function. So for the other of the functions or for the project operators, we still use Velox. And when Velox calculates the project and calculate the function, UDF functions, we convert the necessary columns over this function. So for example, if we have one column, we don't convert that, just send it to Velox, send it back to GVM. And if we have two columns, we do a simple column to row, and then send back to Spark. Send back to the GVM, and the GVM call the UDF functions, and return the data in row format, and then we convert it to Velox format, and then continue the next operators. So it's a partial project. It's used to solve the UDF issues. And the other one is that the other way to solve the UDF is, of course, to offload or to implement the UDF in C++, but sometimes it's very, very hard. And the Rust control cost model, so it's used to, we want to offload when we should fall back, when we should offload. And it's not always that Velox can have better performance. For example, Q72 of TPCDS, vanilla Spark actually has better performance. So we need a way to detect how under which condition we should fall back to vanilla Spark, and under which condition we should use Velox. So it's what Rust is about. And in this year, there are many new features implemented again. And the first one is the state-level resource adjustment. So one big issue of Gluten is that when we allocate the memory, vanilla Spark uses on-heap memory more, but Gluten uses all off-heap memory. It's allocated by all the memory allocation is happening in Velox. It's off-heap memory. And when we implement the Gluten, when we use the Gluten to run a query, sometimes for some states it have to fall back to the vanilla Spark. Then we have to configure a large on-heap memory. But for some other states, we already offload all the states to Velox. In this way, we have to configure a large off-heap memory. So the Velox memory, consumed memory is much less than vanilla Spark, but it does solve some with to finish the query, we have to configure a large on-heap memory and a large off-heap memory. And eventually, the memory consumption is even bigger than vanilla Spark to run these queries. The state-level resource adjustment is used to solve this issue. So we detect that these states have fallback. Then we fallback these states to have fallback operators. We fallback the whole state to vanilla Spark. And then we restart the executor using more on-heap memory. And after these states, then we start the executor use off-heap memory. So we change the executor profile. It's already supported since Spark 3. We change the executor profile and use the Spark's dynamic resource allocation feature to allocate a new operator or new executor to fulfill the on-heap or off-heap requirement. So this is how the state-level resource adjustment works. And then it's the query trace. Query trace is used to, so in Gluten, we need a way to easily debug or optimize the Velox operators. So, but if you run a query using Gluten, it's very hard. It's on top of Java. It's lots of. We need a way to offload or to reproduce the logic, the whole logic in C++, and we can use the C++ benchmark to run in native. And previously, we already implemented the state-level benchmark, so we can dump the data before. After reduce the reader data, so we dumped it. And then we dump the query plan over the whole state. And then we use the input data and the query plan to reproduce the whole state in Velox. We can do that in single thread or multiple thread. And that's one feature we use to do the optimization or to debug Velox. And the other one is that Velox recently added a new feature. It's the query trace. So it can be used to trace the single operator, not only the whole state. You can select the hash join or select the project to trace it and implement that. It's the query trace we added to Gluten support. And the Java 17 support, it's a new feature, and also there are several guys in community to start to add the ARM support. So currently the ARM support, the Gluten can run on ARM machines without any issues. And also, one big feature, we created a POC over the GPU, and we just upstreamed, I think, last week. It's through the CodeDF, thanks to Greg and the NVIDIA team. And also, the other big feature, we started the Flink support. It's talked many times with the Gluten customers, so they wanted to use the same way, use Velox to offload the Flink operators, the SQL operators. And, but we don't have any resource on that. And recently, one company in China, they started the project and they created a POC, and the POC is under review, active review. And one thing I wanted to highlight is that 2025 is a new start. It's a new journey start to the Gluten project, to me and to the Gluten team, to the whole community. Okay, this is the current status of the community. So there are more than 163 contributors from more than 25 companies, and there are 1.3 stars and keep growing. And we have the Apache Slack, the ASF Slack channel created, and we also have the WeChat group. So currently, most of the Gluten users are still in China. And we also created our linked page and we have the Slack, Velox Slack channel. So the Gluten adoption. Gluten is already used. We know the Gluten, Velox itself is used in Meta. It's very mature. So it's much more mature than 1 year ago. And the gluten Velox is known to be adopted by more than 10 companies. So, but in the WeChat group, we have more than 400 people, I think. Almost every Chinese companies who has a Spark cluster, they already tried or already adopted gluten. But most of them didn't ping us or they ping me, but I don't have time to cover. So it's already used there. And because the gluten is designed to not fully replace the Spark SQL engine. So in their adoption, they offload parts of the queries and with the performance gain and fallback the rest with some other queries. Currently, most of the companies, they still use a manually set. So they set a couple, they manually detect this query and should fallback that query should offload. So they manually set it up. And the gluten and the Spark can run on the same cluster, definitely. So it doesn't need any extra requirement over the hardware. It runs the same hardware they can use. So the query, they can switch the gluten and the Spark SQL engine seamlessly on the same cluster. And here is some cloud providers used. Ali Cloud, they joined the gluten community very early. I think it's when we started gluten, 2 months later, they ping me and they start to contribute. MS, Microsoft Fabric, and Google Datadog, there will new session later. And we are working IBM, Watson X data integration now, and there are more to come. And the gluten ClearHouse is used mainly by Killigence and Big O, the two Chinese company. So what I want to highlight is that the gluten currently is already running on several nodes in those big clusters. So some of our customers told us it's really amazing. The performance is very good. Like Meituan, they claimed 40% of the resource saving. It's amazing. And there are some common issues, obviously, we cannot solve everything. So first one is the functionality. So exceptions occur when the operator should fall back, but it's not. So sometimes we solve this issue still. And the result mismatch issue is another big issue. So the vanilla Spark is not a standard, a SQL standard, but sometimes it also has a bug, but we need to make sure that the gluten result, the Velox result match the vanilla Spark result, even it's not correct. So we have to make that in this way, the Spark team can tell their customer, their business customer, that you can use gluten transparently. It's transparent to you. You don't need to worry about the results. And but until now, we still see many cases the result is different actually between vanilla Spark, and we are trying to solve that. Another one is still the memory issues. We tried our best to under CPU support, under off-heap support, under on-heap support, but currently sometimes we still see the gluten task or gluten executor is queued by Yarn or OS or global OEM. The main issue is that the Velox should, or vanilla Spark should track every big block of memory allocation. So all the big block of memory allocation should be tracked by Spark. And in the framework, when the Velox use the Velox memory pool API to allocate memory, then we can make sure that it's tracked by vanilla Spark. But actually, it's many memory allocation is not using the Velox memory pool, and it's not tracked by vanilla Spark. In that way, it's counted into overhead memory, and eventually cause OOM or killed by Yarn. And also, we noticed some performance issues, and the first one is the spill performance issue. The spill. Once the query has spill, the performance is not good. And the sort, we noted that the sort operator in Velox is not faster, or n times faster than vanilla Spark. It's almost the same as vanilla Spark. And then it's a column to root column with a complexity type. And the complexity type is used more and more, but unfortunately, we noted that with the complexity type, the performance is still not as good as we expected. And this is the gluten benefit, the performance boost benefit. So this is, the test is on AWS for R60 ID to X large instance SF500 on TPC8 and TPCDS. And we will upstream this script to Gluten and upstream so everyone can reproduce the performance number by yourself. And one thing to highlight is that we, in Vanilla Spark and Gluten, we use different partition numbers. And we use 2 times over or 4 times the bigger partition number in Vanilla Spark than Gluten to keep no spill triggered on both. So both Vanilla Spark and Gluten, there is no spill here in this test. And the Gluten is 3 times better on TPC8, and the TPCDS is 2.53. And this is tested on Spark 3.5. And the gluten benefit is not only the performance. Actually, the more important benefit comes from memory utilization. From this chart, you can clearly see that when we run Vanilla Spark and the gluten, and you can see that the used memory in Vanilla Spark is almost 80%. Actually, it's already triggered a spill in this test. But in gluten, it's under 20%. It's under 20%. Only Q21, the performance is the memory is close to 80%, but no spill triggered. There in Vanilla Spark, it's also 80%, but it's already triggered a spill with a spill. So here we use the same partition size over gluten and the Vanilla Spark, which means that the customer can configure their executor with half or 1/4 of the memory Vanilla Spark used. And if they configure the same memory, then less spill will happen in gluten, and the performance is boosted again. If they configure less memory for each executor, then they can start more executors on the same cluster. It's because that the common case over Spark runtime is that the memory size is the limitation. The CPU number is not, the memory size is. So once they decrease the memory size, more CPU will be used on the cluster, and then they can get better performance. So they impacted each other. And also we noted that especially on the cloud, because on the cloud, the memories, the S3, like the S3 throughput and the network throughput, it's already there. We cannot change. And to Spark, we may say that, okay, CPU utilization is very high, and it's good. The memory throughput, the network throughput is not a big issue, or the disk is not a big issue. But when we run gluten, because the gluten is 3 times faster, in theory, it also needs 3 times more throughput over S3 and the network. But on the cloud, it's not possible. It's limited. And when we run the Spark, when we run the gluten, we can see that the I/O will become bottleneck commonly, and the CPU utilization can decrease. In this way, we can still save the power cost. Okay, this is the roadmap, the same roadmap over this year. In this Q1, we focused on the performance track on AWS. Previously, we don't have this environment, we don't have this budget. Now in IBM, we can do these things. We keep track of performance on AWS. And then we ported the Iceberg UT. We added Iceberg hoodie and the data lake support last year, but actually we didn't port the UT. We didn't pass the UT. It just supported the basic reading, memory, the file reading, the partition reading, but it's the UT is not passed. This year, this quarter, we take some time to port the UT and pass the UTs. And there are many UTs still failed. We still fallback. There are many UTs fallbacks onto Vanilla Spark actually. And the Velox upstream, we're still working on this and the state level resource adjustment. And we started the first GPU POC here. That's the implement. Under Q2, we will focus on documentation, dictionary shuffle. Dictionary shuffle is used to decrease the shuffle data size. In this way, we can get better performance because the shuffle data size decreased. If your bottleneck network is a bottleneck, you still can get the performance. And the storage memory. Storage memory is something we didn't support until now. And in Vanilla Spark, it uses execution memory and the storage memory. It can adjust it between each other. But actually, we already use execution memory. And the Spark 3.4 support once it's become released. Currently, it's still not released yet, officially released yet. Under PHG, and then in Q3, we will under PySpark, because PySpark, especially Spark 3.4, there are more features coming in the PySpark. And Iceberg, we will under Iceberg write support. Currently, Iceberg write actually for back to Vanilla Spark, and we will under that to Gluten, under Hoodie Data Lake UT, and then Q4, we will under Hoodie our more PHG optimizations. And one big thing to happen in Q4 is that we plan to graduate from Apache in Q4. And this is currently. I want to highlight the accelerator support. So in accelerator support, we have two ways actually. One way is that we send the substrate plan to the accelerator, and then the Velox convert the data to Unroll and input the accelerator, get the Unroll data output, and then send to the Velox. It's one way to support. Currently, we supported from QDF is in this way. The Velox will offload the operator to QDF. We can control that. When we convert the substrate plan to Velox plan, we select the QDF operators or the Velox operators. We select that, and then Velox itself will handle the data conversion, will handle the GPU calls, everything, and then get the data back to Vanilla Spark, to Velox. We created the POC is already upstreamed, so the performance is still not good. Definitely, we just passed the POC, created the Docker. It's a start. I think it's a start. And the Flink support, I just presented. The POC is already created in community, and we started working on that. The community actually working on that. Okay, I think that's all the things I want to talk today. And if any questions, I don't. Yeah. Sorry. Wait. Yes. Yeah. The binary release doesn't have. The binary release is all x86, but we can add that. Yeah.
When you showed the timing differences, what percentage of that work is like bioscans, where that might be harder to achieve, and what percentage of that work is like doing other things where you probably could expect greater performance increases? So in those workloads that you were looking at.
Yeah, so for the workload, definitely the hash join, the prefer scan, hash join, and the hash aggregate, they are the main operators, so we can get the performance. And here, if we compare to the Vanilla Spark, one tricky thing we actually do is that we use more hash join. We use bigger broadcast hash join threshold. So the current plan is a bit different. And when we compare the hash join of Velox with the Vanilla Spark, the sort merge join, the performance definitely is much better. Yeah, but we can support that because Velox itself supports spill in hash join, but the Vanilla Spark doesn't support the spill in hash join. It only supports sort.